Drop a block of solid aluminum into a tank of water, and physics dictates exactly what happens next. It sinks like a stone, victim to its own density and the relentless pull of gravity. But in early 2026, researchers demonstrated something that looks like a glitch in the simulation. They dropped a piece of specially treated aluminum into water, and instead of sinking, it bobbed on the surface like a cork. This isn't a magic trick, and it's not a hollow shell. This is solid metal that has been fundamentally re-engineered at the surface level to wage war against the very nature of liquid. To understand how this works, we first have to look at how water normally behaves. Water molecules are incredibly social. They love to stick to things, a property we call wetting. When water touches a standard metal surface, it spreads out, filling every microscopic crack and pore. This creates a direct bond between the liquid and the solid, allowing the metal's weight to take over. Engineers have tried to stop this for decades using chemical coatings like the nonstick spray on your frying pan, but coatings eventually wear off, scratch, or fail under pressure. The breakthrough in 2026 moved away from chemicals entirely. Instead, researchers looked at the geometry of the surface itself, taking inspiration from nature's own master of water repellency, the lotus leaf. If you look close enough at a lotus leaf, you'll see it's not smooth. It's covered in tiny, microscopic bumps that prevent water from ever actually touching the leaf's surface. The challenge for engineers was simple but daunting. How do you recreate this delicate biological architecture on a piece of hard industrial aluminum? The solution came from a tool of incredible precision, the femtosecond laser. These aren't your average cutting lasers. They pulse at speeds so fast they're measured in quadrillionths of a second. At this speed, the laser doesn't just melt the metal, it causes the atoms to instantly vaporize, a process called cold ablation, leaving behind a perfectly sculpted landscape. By firing these pulses in specific patterns, researchers can carve peaks and valleys into the aluminum that are thousands of times smaller than a grain of sand. This new surface isn't just water-resistant, it's so extreme that it forces a layer of air to become a permanent part of the metal structure. This is where the real engineering begins. Even when you push the metal deep underwater, that air layer stays put. It creates a buoyancy that the metal simply cannot overcome, making it effectively unsinkable. But how does a thin layer of air survive the crushing pressure of the deep ocean? To find out, we have to look at the physics of the plastron. The secret to this unsinkable metal is something called a plastron. In biology, this is a thin layer of air trapped by hairs on the bodies of certain aquatic insects, allowing them to breathe underwater. By mimicking this with laser-etched nanostructures, engineers have created a synthetic plastron. The air isn't just sitting there, it's being held in place by intense physical forces. Think of it like a bed of nails. If you try to push a balloon onto a single nail, it pops. But on a bed of thousands of nails, the pressure is distributed and the balloon stays intact. At the nanoscale, water has a very high surface tension. It acts like a stretchy rubber skin. Because the gaps between the laser-etched peaks are so small, the water's skin is too stiff to bend down into the valleys. This is governed by the Laplace pressure. As the gap between the peaks gets smaller, the pressure required to force water into that gap increases exponentially. By keeping the peaks just a few hundred nanometers apart, the researchers ensured that even under significant depth, the water simply doesn't have the energy to break the surface tension and displace the air. But the peaks and valleys aren't just random, they are hierarchical structures. This means there are large structures with even smaller structures built on top of them, creating multiple levels of defense. This hierarchy is crucial. If a few nanostructures fail, the larger structures are still there to trap secondary pockets of air. It's a redundant system that makes the plastron incredibly stable. The result is a surface that is super hydrophobic in 3 dimensions. It doesn't just repel water from the top, it repels it from every possible angle of attack. To create these structures, the laser has to be tuned perfectly. If the pulse is too strong, it melts the peaks into blobs. If it's too weak, the valleys aren't deep enough to trap enough air. The researchers found that a specific crosshatch pattern worked best. By scanning the laser in 2 perpendicular directions, they created a grid of air-trapping wells that are much harder to displace than simple ridges. This geometry is the key to the unsinkable property. It's not about the material, it's about the shape of the space where the material meets the world. The physics here is so robust that the metal can stay submerged for months without losing its air layer. In lab tests, even after being forced underwater for long periods, it popped back to the surface the moment it was released. This is a fundamental shift in how we think about buoyancy. We're no longer relying on the density of the object, but on the physics of the air it carries with it. But as brilliant as the physics is, the real world is a messy place. And for this technology to leave the lab, it has to survive more than just a clean tank of water. The biggest enemy of any nanostructure is physical wear. Those tiny, sharp peaks that trap the air are incredibly fragile. A single scratch from a grain of sand can crush thousands of them instantly. If the peaks are flattened, the air layer vanishes, the water rushes in, and the unsinkable metal finally sinks. This is the Achilles heel of the technology that engineers are currently racing to solve. To fix this, researchers are looking at self-healing structures or protecting the nanostructures inside larger, tougher microgrooves that act as a roll cage for the delicate peaks. But even with the durability challenge, the potential applications are staggering. Think about underwater sensors. Usually, saltwater is the enemy, causing corrosion and biofouling almost immediately. Because the water never actually touches the metal of a plastron-treated sensor, the chemical reactions that cause rust simply can't happen. It's like the metal is in a permanent vacuum, even at the bottom of the ocean. This could lead to sensors that last for decades without maintenance, monitoring everything from ocean temperatures to tectonic shifts with zero degradation. And it's not just aluminum. The femtosecond laser technique can be applied to almost any metal: steel, titanium, even copper. Each material presents its own unique challenges and opportunities. Imagine a ship hull that never needs anti-fouling paint because barnacles can't stick to air, or a submarine that moves through the water with almost zero friction because it's sliding on a cushion of bubbles. The fuel savings alone for the global shipping industry would be massive, potentially reducing carbon emissions by millions of tons every year. We are entering an era where we don't just accept the properties of materials, we design them from the atoms up. The unsinkable aluminum is just the beginning of this journey. Researchers are already looking at how to make these surfaces active, using small electrical charges to expand or contract the air layer on command, effectively giving the metal lungs. This would allow a piece of metal to sink or float at will without any moving parts, pumps, or ballast tanks. It's solid-state buoyancy. Next time you see a heavy piece of metal, remember that its weight is only half the story. With the right geometry and a little help from the physics of the nanoscale, even the heaviest materials can be taught to defy the water. The engineering behind the plastron shows us that the line between the possible and the impossible is often just a few hundred nanometers wide. We are finally learning to master the interface between the world we see and the invisible forces that govern it, and that is where the real magic happens.